Okay, let's get started. So today we will be discussing a variety of different security issues with large language models. So we'll be talking about things like distilling language models, extracting them, and if you have your own small language model at home, how can you use OpenAI's API to make your own language model better? These are all things at the forefront of the leaders of all these companies who have released their models today. And there have been a lot of successful applications of some of these techniques to get better performing small scale language models that are useful for like small companies or academic research. So before we start, just a word on the exam grading. So we will finish the grading of the exam by the end of next week. As you can imagine, it's not very straightforward to grade with such open-ended questions. We will do our best, and after we release the grades, you will have 1 week to raise any regrade requests that you might want, and yeah, we'll take care of those at that time. Another thing I want to say is regarding the assignments for the rest of the class. So you'll have one more homework that should go out within the next week. It'll be kind of a hybrid between using some of the Hugging Face libraries to fine-tune a model like BERT, and also will involve a component where we ask you to prompt one of these large language models like ChatGPT and create your own small data set of questions that these models cannot answer. So it's kind of like half data collection and analysis and half getting some hands-on experience with using the models. It shouldn't take too long or be too stressful. Yeah. Yeah, so regarding the midterm, we will go over all of the answers once the grading has been complete. Usually I like to, say what the common answers in the class were to each problem and things like that. No answer key will be released, but we will go over it in the class itself. And yeah, the big deliverable that you have left is your final project reports that are due May 17th or something like that. So you should be spending most of your time for the rest of the semester working to accomplish your stated goals for that project and writing up your report and so on. So from now till then, there will be more quizzes every week. So we kind of just punted on that for a couple months. But we will have about a quiz every week, and we will have one this week as well. So remember those, you just submit on Gradescope by the specified due date. There's no check for correctness. All right, any questions about, yeah? Are you talking about the image generation models? Yeah. So we will have one lecture on vision and language models. Of course, we won't spend a lecture talking about diffusion models. If you take a computer vision class, you will probably cover that. But yeah, we will talk about things like CLIP and some of the more recent models as well. In computer vision, people are using things like the visual transformer to encode images and do predictions and generate images. So a lot of the stuff that you've learned is applicable there. But yeah, I mean, the dominant approach to generating images is through diffusion models, which we will not cover in this class. Yeah, so that is, it will be out probably by the time we finish grading your exam. Yeah, I still have to give the rubric to the graders. It's on me. Other questions? Oh, I should, okay, so no questions on YouTube. Okay, so let's get started. So the scenario for this, this lecture is the one that you all probably had when you tried to use ChatGPT for your exam. You have an API, black box. You have no idea what the inner workings of the model are. You just have the ability to type stuff into the model and get an output, like a generated sequence from the model. So in particular, you have no access to the hidden states of ChatGPT or GPT-4. You don't even know what the probability distribution over the next word is. Like OpenAI explicitly does not provide this for their newer models because providing this makes it more easy to distill their model, as we'll see later on in this lecture. For a model like GPT-4, you don't even know the size of the model, you don't know the architecture, it may not even be a transformer, we have no idea. You don't know the composition of the training data or how much data it was trained on. So in a nutshell, you are missing like extremely crucial details to reproducing these models. And the reason why you don't have this information is because OpenAI and other companies deem it as a competitive advantage, right? So if they publish how big their model is and what data it was trained on, then what is stopping Google from simply replicating the setup and getting an equally as good model, right? So because they want people to stick with OpenAI, they want at least some layer of obscurity to be over the actual details of their model. However, even this setup makes them liable to outside users attacking the API just through input-output queries. You can learn a lot about the behavior of the model. And this is not something that OpenAI can really control because you're always going to have to at least let users interact with your model through some interface, right? So this lecture will focus on, even if you have minimal possible signal from this language model, like specifically you have only generated outputs, how can you use these outputs to make your own better language model? So a concrete question. Imagine you have a very small language model, like one that you can run or train on Colab yourself. How can you improve this tiny model using GPT-4? Right? And of course, OpenAI would love if there's no way for you to improve your model, but that's simply not the case. So the first concept that we'll cover in this lecture is knowledge distillation. So this is a critical concept when you're talking about extracting a model that is served by some sort of black box API. So in this setup, you have a small model, which is usually called the student model. And you have a much larger model, which is the teacher model. So you can think of the teacher model as being inaccessible. You can never create one yourself, but you can query the teacher model. Say it's like a GPT-4. You can submit queries to this model, get outputs, and hopefully you can use that in some way to teach your student how to do better. So let's take a look at how this works in the context of BERT. So remember, BERT, again, is an encoder-only pre-trained transformer. The pre-training task for BERT is to predict the identity of a masked token in the input sequence. So we saw this slide before. Bob went to the mask to get a buzz cut. Now, let's say you have a teacher model, which is this 24-layer BERT large. This thing will spit out a probability distribution over the next word, right? And the key idea with the basic form of distillation is that I can use the probability distribution produced by the teacher model to fine-tune my student model. The idea is that if I was doing this just as a normal pre-training task, I would only have the correct identity of this word in the mask token, right? So maybe I have a sentence like Bob went to the barber shop to get a buzz cut. So remember how we pre-train this BERT model. We say that the ground truth distribution that we want to predict has 100% of the probability on barber shop and a 0% probability on any other word in the vocabulary. So in some sense, this is obviously this is maximizing the likelihood of the training data, but it's not really realistic in many contexts, right? Like maybe barber is an equally valid word, it just didn't happen to be the word that was used in the sentence you observed in your training data. So instead, imagine your task for your student model is you have Bob went to the mask to get a buzz cut, but instead of predicting the single word barbershop, instead you're trying to match the distribution over the entire vocabulary that is predicted by the teacher model. So your model is not trained to put 100% probability on barbershop. Instead, it's trained to put 54% probability on barbershop, 20% probability on barber, 6% on salon, and so on. So you can train the model to mimic the distribution that the teacher model has produced. Does that make sense? Does it also make sense why this intuitively might give you more signal as to, you know, the context here than just predicting what is in your training data with 100% probability? Okay, so these targets for the distillation are generally called soft targets. They're soft because you have a full distribution over the entire vocabulary. Each word in the vocabulary has some non-zero probability, and the model is trained to replicate those probabilities. This is in contrast to hard targets, which is what you traditionally observe during pre-training, where you have a sentence, Bob went to the barbershop. Barbershop is your only target, and you want to maximize your probability of barbershop. That is not the case during distillation. In distillation, you have soft targets. So basically, you're trying to train your student model to behave similarly to the teacher model. And by behave, I mean output a distribution that is similarly shaped. Okay, yeah?
Just a quick question, because like the salt question we had in the previous slides, so say that we are trying to like improve our model based on like GPT-4, but we don't have the soft like distribution.
Yes, this is a great point. So this approach cannot be used for extracting GPT-4. The reason is we don't have soft targets for GPT-4, right? OpenAI knows that people could easily do this if you provide access to the soft targets. They didn't even give this access with GPT-3. They give you access to like the top 5 or top 10 most probable words, but that's it, not the full distribution. We will talk a little bit later on about how you can perform these kinds of extractions without access to the soft targets. This approach, knowledge distillation, is not necessarily only useful when you want to like steal another model. It is also useful if you have constraints on, like, let's say I can only run a 4-layer model in my production because of latency requirements. Like, it has to be fast. I can run a max of a 4-layer model. I will never be able to get a 4-layer model trained from scratch that works as well as one that has been distilled from a much larger model. This is generally the use case of these things, as we will see in this slide. So there are several approaches when BERT came out to try and make BERT smaller so that it could be more useful for people who had inferior GPUs or companies that wanted to serve it to a lot of users. In particular, there was this method called DistilBERT. So DistilBERT essentially takes this teacher BERT model, which might be 12 or 24 layers, and it makes a student model of half the size, or even less than that. And the way it's trained is that for a given input text, you mask out some words, then you get the distribution over those mask tokens under the teacher model. So you have, for every mask token, a distribution that looks like this that comes from the teacher model. Now you take your student model and you just compute the cross-entropy loss between the student model's prediction and the teacher's soft targets. So remember, we talked about the cross-entropy loss before when we were maximizing the likelihood of our training data, and we found that because 100% of the probability was on the ground truth token that appears in the training data, the cross-entropy loss was the same as the negative log likelihood of the target token. In this case, that's not true, because you don't just have 100% of the probability on one word, right? Now you have a full distribution, and so every single word is included in the computation of the cross entropy loss. Okay, any questions about this? Yeah. Yeah, so here I'm only talking about cases where the student model is smaller than the teacher model, but there have been cases where people train a student model that's even bigger than the teacher model. And in this case, the student model does, in some cases, outperform the teacher model. This work has been shown primarily in computer vision, not in NLP, but it is a thing. So you can kind of bootstrap better and better models by using like your previous model as a teacher and using it to train an even bigger model. But yeah, it's kind of unintuitive why this might happen, but it seems to work in practice. Yeah, sure. Other questions? Yes.
Given that the smaller student model is able to perform as well as like a larger model, why is it hard to train just a small model to start with the same?
So this is a good question. So the question is, why can't I just train a 6-layer BERT from scratch that achieves the same performance of the teacher model? The intuition behind this is that the distilled 6-layer model has access to a lot more information about the training data than the train from scratch model, just because the distilled model, you can even see in this example, right? You are encouraging it to not only predict barbershop as a high probable word, but also upweight barber and salon and stylist, which are all reasonable choices to fill in this mask token. But if you're training from scratch, you only observe one word that could be used. So there's a gap in the amount of information that each type of model is given. Yeah. Yeah, this is a great question too. So we are saying DistilBERT is a 6-layer transformer. Is that thing initialized from scratch? Generally, no. So there have been many studies on like what is the best way to get this student model, but what generally is the best is to pre-train the student model from scratch, like he suggested. So you get like an inferior model to the teacher, obviously because it's smaller, but it's still pre-trained on this. And then you can fine-tune that model using the targets from the teacher model. So pre-training is very important during this process. Can the teacher model weights be pruned down to the size of the student model and still retain the same performance? Yeah, so we won't talk about pruning in this lecture, but it is possible in some cases that you can, in fact, get rid of entire layers of the network after training because they don't contribute that much to the performance of the resulting model. Especially during fine-tuning, you can do things like this. But yeah, pruning has been explored extensively with these transformer models, not only things like pruning or ignoring layers, but also removing attention heads and other things like this. I think in practice, it's been very hard to implement these pruning methods to actually see measurable speed gains. Like the only reason you would want to prune a model is to make it faster at inference time. But you can imagine if I prune 3 attention heads, this is not going to really give me that much speed up unless my implementation is, like not parallelizing all of the attention computations, which it is doing in, like PyTorch or whatever normal implementation you're using. Okay, what is the advantage of using DistilBERT over BERT? The advantage is that DistilBERT is much smaller, so it's faster at inference time. So let's say I had millions of users querying BERT at the same time, right? Obviously, I would want to use a much smaller model if I could retain the performance of the bigger model, because then I will need to use less compute. Also, if I have like a obsolete GPU, right? I might not be able to run a 24-layer transformer, but I might be able to run a 6-layer one. Okay, so just to summarize, instead of the one hot distribution of the target token that we observed in all of the previous classes when we talked about training language models, here we have a full, complete distribution over the vocabulary where every word is associated with a non-zero probability. So there's more information, again, back to your question, encoded in this target distribution than in the one hot distribution. And even like some very low probability words, there's useful information encoded there. So for example, here, Bob went to the blank to get a buzz cut. The word church would be very low probability here, right? Because you don't really go to churches to get haircuts. But it should be higher probability than something like and, which doesn't even make grammatical sense in this context. So even like these two very, very low probability candidates, the order of those could tell you a lot about the, the context that this mask token occurs in. Okay, so we should talk a little bit about performance. So generally speaking, a smaller student model will be worse than the teacher model. There will be some degradation in performance. So DistilBERT, they write, retains 97% of the original BERT teacher model's performance on a bunch of different downstream tasks. So you can see here that averaged across this glue benchmark, which contains a bunch of different sentence level classification tasks, BERT base gets a score of 79.5, DistilBERT gets a score of 77. So there is some performance drop, but it's not significant. If you look closely at the paper or related papers, you will see also baselines where they just train the 6-layer transformer from scratch. These do significantly worse on this benchmark. So distillation is very useful compared to training from scratch. And so far, we have just talked about distilling the final predicted distribution. So, we have our teacher model. It computes all these different hidden states at different layers. And then finally, it computes a distribution over the whole vocabulary. And so right now, the approach we've described just does the distillation at that distribution level. So we have a student model with all of its hidden states. It spits out one distribution. We have a teacher model. It spits out another distribution. We compute the cross-entropy loss and fine-tune our model that way. But this means we're ignoring many interesting components of the teacher model, right? Like, what about the hidden states of the teacher model or the attention maps at each layer? Those parts of the teacher model might, contain a lot of useful information that we could transfer to our student model. So this paper called TinyBERT additionally does distillation on the intermediate representations of the models. So for example, you can just devise a mapping between the layers of the student model and the teacher model. So for example, maybe layer 1 of the student model maps to layer 1 of the teacher model, layer 2 of the student model might map to layer 4 of the teacher model, and some arbitrary mapping like this could be devised, and then you could just try and make the attention maps, the attention scores of the student model at layer L as close to the teacher's attention maps at the corresponding aligned layer as possible. So you can do this with the attention matrices, with the hidden states, with many other components of this model. So let's say you were trying to do distillation on the hidden states. So let's say you get the hidden states at layer 1 of the student model, you get the hidden states of layer 4 of the teacher model, and you want to make those as close to each other as possible. How would you implement this?
The same size, you get the weights and biases for each one to be
Okay, so one thing you said is important, right? Ideally, those representations would be the same dimensionality. So let's assume that the hidden states are of the same dimensionality. So you mentioned doing the cross entropy loss, but is that the right loss function when you have one continuous vector and another continuous vector? These are not distributions, remember. So the hidden states are not probability distributions. They're just like, dense vectors. So in that case, what loss function might you want to use? Sure, so cosine similarity is a reasonable objective function. You could also use the square loss, which we discussed before. What's that? Oh, you said the Euclidean. Oh, I thought you said equivalence. I was like, yes. So that is, any of these like vector similarity functions are totally acceptable for this kind of distillation. Even with the attention matrices, you can do this. Although, since those are distributions, you could also use the cross entropy loss row-wise to do the distillation. So if you do it this way, they show that you can get even, close the gap to the teacher model even further than just distilling the final probability distribution. So these techniques are generally very useful for, especially for people that don't have access to these huge scale computational resources. Mm-hmm. Yeah, so if the hidden layers are not the same size, then it becomes much harder to do this. You can always put a linear layer over whichever model is, let's say, over the student model to make it the same dimensionality and then apply the loss. But that is just adding an extra parameter, which might not be useful. So in general, the scenario in which distillation is useful is that someone has already created the teacher model, and they put in a lot of expense to do so. So you can design the architecture of your student model to be best suited to distillation. So for example, you could choose the same hidden state dimensionality as the teacher model and just have fewer layers or something like that.
This relies on information like hidden states, the size of the potential rates
Yes.
to be available, right?
Yes. So again, this is not possible with, say, GPT-4 because we don't even know how many layers it has or if it is even a transformer, let alone have access to the hidden states or the attention weights. So again, this is not really practical from a attacking an API perspective, but it's very useful if, for example, the teacher model is a large open sourced model. So for example, Meta released this OPT model, which is 175 billion parameters. No one can really run that on, your gaming laptop can't run this thing, right? But if you were able to distill it into, say, a billion parameter model or something like that, then, maybe it becomes very useful. So yeah, that's a good point. Other questions? Yeah, that's the easiest way to make this happen. So the student might just have fewer layers, but the structure of each layer is the same, the hyperparameters. Okay. So this is a great paper studying the different ways in which you can combine pre-training and distillation with BERT models. It's called Well-Read Students Learn Better. The title alone suggests the conclusion of the paper, which is that if you do pre-training on the student model before distillation, you get a much better resulting model. So here, the X, this gray dotted line with the X's that is at the bottom of every plot, this is the performance you would get with a model trained from scratch without any distillation or pre-training on one of these 4 downstream tasks. So you can see that it's worse in every single case. Training from scratch, generally not advised. Then we have the distillation approach. So this takes the teacher model and it distills the predictions on these classification tasks into the student model. And the best performing approach is pre-trained distillation. So you do the distillation both during pre-training time, this is for masked language modeling, and at fine-tuning time when, let's say you're doing sentiment analysis. Your teacher model can give you a prediction of probability distribution over positive and negative. You can distill that too. So you can do this distillation both for the pre-training task and the fine-tuning task. So I'd encourage you to check out this paper if you're curious about applying any of these methods. As you can see, the choice that you make regarding when to pre-train and how to pre-train and fine-tune can make a big impact when you're doing distillation. Okay, so yeah, I had some more slides about this, which I'll probably skip. I wanted to talk about some of the questions that have been brought up so far, which are, well, this is all great, but we don't have access to any of this information with the models that we actually are interested in distilling, right? We might have, for instance, only the prediction of the returned by the API and no access to its training data or even its model architecture. So what do we do in this case? So I'll talk a bit about some works by my own lab that operate in this space, and I'll also talk about some very recent work on extracting models like ChatGPT and GPT-3, which should give us all some hope that we can also one day get access to these kinds of models. The first work I'm going to talk about is focused on BERT. So this work was done a couple of years ago, back when BERT was considered like the largest and best model. Now, of course, BERT is like obsolete already, how quickly things have changed. No one would ever want to extract BERT because you can just like run it on your MacBook probably now. Anyway, so in this work, we also are operating under this model extraction attack framework, which is very similar to distillation, but it differs in the sense that you don't have access to the training data that the teacher model was pre-trained on or fine-tuned on. And you also may not have access to the probability distribution that the model produces. So many companies have these kinds of NLP APIs, you know, like Google, Amazon, Azure, all of these cloud providers have an NLP service where you can pick a task like sentiment analysis. You can query their API. This is a great movie. There's some black box model. You don't know what it's doing, but it will give you some label like positive or negative. And so these companies make a lot of money on these services because they can charge by the query like some fixed rate. And so one scenario that might be of interest to an attacker is, let's say I have a fixed budget of $100 and I can issue this many queries to this model, to this API with my budget. How can I use those queries to best extract my own sentiment classifier that performs similarly to this one? If I can get such a model, I don't have to use this API anymore and I don't have to pay for it, right? So we call the model that we want to extract the victim model. So basically we want to obtain something as close to a copy of this model as possible. At least its performance on the downstream task should be very similar to that of the victim model. So the strategy that we explore here is very stupid, but it is also effective. So remember that you don't have any access to the training data of the model. So one question is, how do you form a meaningful query to the model? Right? So for sentiment, it might be easy, right? I can just grab any sentence from a review posted online, send it to the API, and then I'll have access to the sentiment prediction. But in general, this might not be so simple, right? What if I have a very complicated task where it's hard for me to even devise these inputs and have, you know, like hundreds of thousands of queries? What if we want a method that's kind of agnostic to the task? So we look at two simple approaches. One is you just sample random sequences of words from the vocabulary that aren't even grammatically correct. So I could, for example, feed in 17 dot miles Vegas. This is completely meaningless, but the model will give you a positive or negative prediction on this sentence, similarly to this one. Another approach we try out is what if you just sample some arbitrary sentence from Wikipedia, regardless of what the task is, and get a prediction. But neither of these methods requires any knowledge of the task, right? You're just giving it some input and seeing what label it produces. So maybe the model thought 17.3 miles Vegas was positive and circle Ford had support wife rulers was negative, right? Again, these don't mean anything to us, but if you have like hundreds of thousands of these kinds of queries, perhaps you can actually extract some meaningful signal as to the model's behavior. So let's say you extract like hundreds of thousands of these gibberish inputs and labels from the API. Now I can take my own pre-trained NLP model. So let's say I have my own BERT model that I downloaded from Hugging Face. I can fine-tune that pre-trained model using these gibberish input queries paired with the label that the API returned. Note that this setup requires no knowledge about the task itself, the data itself, or the identity of the victim model. It just requires inputs and outputs from the API. Somehow, it turns out that this extracted model, despite not seeing any real sentences during this model extraction phase, works well on real data. So if you put in "this is a great movie," it will predict positive even though it never observed real sentiment-containing sentences during fine-tuning. And of course, this is a big problem for companies because these attacks are very cheap. So we did all the attacks in this paper for like $200 on many different NLP APIs. And obviously, if, for example, Google puts in a lot of money and personnel on training such a model and then releases it behind an API, and then someone can just, with $200, replicate it, this isn't a great business model at all. There's also issues with privacy that could arise. So maybe now some of those queries can result in leakage of the training data. It could also help generate adversarial examples, which could be transferred over to the original victim model. So there's many issues with this kind of model extraction. So we, for sentiment, it took only $60 to get a model that performed similarly to the Google Cloud Sentiment API. For speech transcription, like $400. And after we published this paper, someone used a similar technique to extract Google Translate, like for many different language pairs, with pretty decent success for only a couple $1,000s. And that paper was done by researchers at Berkeley. It's one of the optional readings for today. It proved to be extremely difficult for them to publish their work, but that should tell you how effective these kinds of simple attacks are. So one of the key takeaways from this kind of work is that the stronger the base model that the attacker starts with, the more likely it is that the attack will succeed. So if I start with a pre-trained BERT large model, this is generally always going to be a better base model than if I use a smaller model. And nowadays, you can start with very, very powerful base models. So for example, as we'll see in a bit, Meta released these models called Llama, which have been pre-trained on an enormous amount of data. And the models are open source for research purposes. So you can download that model and then fine-tune it on data generated by GPT-4 or ChatGPT. Many people have done this already, as we will see, and you get the resulting models are very good. So this is certainly something that companies like OpenAI and Microsoft and Google are worried about right now. So again, this differs from distillation in a couple ways. First, you don't have access to the training data of the teacher model. You may not have access to the probability distribution produced by the teacher model. And your goal is different too, right? Here you want to actually steal something. You don't want to just make it smaller. So I'll maybe skip through some of the details of this approach, but as I mentioned, there are these two ways of generating the data. You can also, like, if you have some task-specific knowledge, you can design your queries in a way to match that, that domain knowledge. So for example, if you wanted to answer questions about a paragraph, right? We saw this with Squad. Let's say there's an API that offers this kind of question answering model. I can create questions by randomly generating a paragraph and then randomly generating a question from using words that are randomly sampled from this paragraph. Obviously, if you read this, it makes no sense. The passage nor the question, neither of them make sense. But the model will spit out some span in the paragraph that is an answer. And so you can see that for Squad, the victim model gets 90.6 F1, and one of our attacks using Wikipedia sentences reaches an F1 of 89.4. So almost no loss in question answering ability, despite not even seeing text from any sort of QA data set. Okay, so as I mentioned, the main finding that is of interest to all of you is that a better pre-trained model, like a more powerful, a larger pre-trained model that's trained on more and more data, will always be a better base model for extraction than a smaller model. So if you could only change one thing, you should choose a pre-trained model that is very strong itself. Okay, so now let's shift a little and talk about large language models like GPT-4 or ChatGPT. Like, you have even less information about these models. How can you apply some of these techniques to distill them? So this is the recipe used by researchers from Stanford to distill GPT 3.5 into a smaller open-sourced language model. So the first step, again, something that's very important is starting with a strong pre-trained model. So they got the weights of Meta's Llama model, which you can apply to get access to. And it's been pre-trained on a lot more data than you could ever pre-train a model yourself on. So it's a very useful starting point. So then step 2 is kind of the critical step here. You extract some sort of data from the API that you can use to fine-tune this model that you got in step 1. So in the previous work on extracting BERT-based victim models, we got this data by just submitting random queries to the API and seeing what label they produce. In the case of something like GPT-4, it's not so simple because the model is generating sequences of text, right? Not just giving you positive or negative outputs. The model can generate many different pieces of text given its decoding algorithm, the hyperparameters, and so on. So you have all of these variables too. And the biggest issue is that these models are just capable of a lot more, solving many more tasks than a model like Google Cloud Sentiment API, right? Which can only do sentiment by definition. So GPT-4 can do an arbitrary number of tasks depending on how you define your instructions. So in this work, the researchers were particularly interested in extracting the instruction following ability of these open AI models. So remember how that ability was even induced into the model. They first pre-trained a giant language model on next word prediction. Then they gathered demonstrations of instructions, inputs, and outputs that they had human labelers like actually write the outputs to a bunch of different tasks, right? So then they fine-tuned their model on these instructions. This was we called instruction tuning. And then they further collected human feedback on the model's capabilities for different tasks. And they further tuned their model using RLHF, right, to make the model even more aligned to what their users wanted. This process goes without saying, it's insanely expensive, right? Every stage is expensive. First, pre-training, incredibly expensive. It requires a lot of compute, requires a lot of data and expertise, engineering expertise, and so on. The second step, instruction tuning, also expensive. You need to hire people to write demonstrations, and you probably want a lot of diversity in the tasks that they're covering, and so on. The third step, finally, RLHF, you need users to give you feedback to further improve your model. So it would be great if I could start with a model that has been pre-trained and just skip over the RLHF and the instruction tuning, but somehow get those capabilities myself, right? So this is the situation where most of these previous works are looking at. So let's take a look at step 2 in particular, because it is the most important step, extracting the data that's used to fine-tune this model in step 1. Any questions before? Okay, so the general idea is that we, as attackers to OpenAI's API, do not have the resources to collect our own demonstrations and instruction tune this llama model. So can we get descriptions of tasks and a corresponding input and output examples from the model itself? Like, can we make the model generate its own tasks that we can then use to fine-tune our model? So this self-instruct paper is a very, very simple way of doing this. I'll just show you prompt. This prompt is from their paper. So remember, the goal is to generate instructions and outputs. So they have a simple prompt. Come up with examples for the following tasks. Try to generate multiple examples when possible. If the task doesn't require additional input, you can just generate the output directly. So, and now there's a bunch of human-written demonstrations of tasks. Task, which exercises are best for reducing belly fat at home? Output, it has some exercises. Here's another task. Extract all the country names in the paragraph, list them separated by commas. Here's a paragraph, here's the, wow, English is not a country name. Anyway, here's the output from, this was actually a prompt in their paper, so this is an error, but whatever. Here's another task. Convert 85 degrees Fahrenheit to Celsius. Sort the given list in ascending order. So here you can see there's 2 examples provided. Again, these are examples, demonstrations that humans have written, but it's a very short list, right? Suggest a more professional rephrasing of the following sentence. So here's a sentence and here's a rephrased output. Turn down a job offer by sending an email to a recruiter explaining the reason, and here's a reason. So basically, this is going to be fed as a prompt to GPT-4, and the goal is to make GPT-4 generate many tasks of its own and also input-output pairs corresponding to each task. So we can try this out on the playground here. So I wrote, let's see, you are a helpful assistant, who is especially good at coming up with creative tasks and examples for those tasks. So you can write something here, and then we'll just paste in our prompt with all these different tasks and examples of the tasks. And now we'll ask it to just generate a new task. So it created this task: create a weekly plan for a vegetarian. and I guess it's going to do this for the whole week, which, God. This might be a pretty long demonstration here. But you can see that this task was not specified in the prompt, but instead the model came up with it itself. And you know, the output looks pretty good. Like these are all vegetarian foods, I assume. Oh my God. It might actually be better than the demonstrations in the prompt that we submitted. So imagine you have a fixed budget that you can use on GPT-4. You could query the model with this prompt many different times. And in the self-instruct paper, they even find that it's better to include some of the model's own generations instead of the human-written demonstrations into the prompt for diversity. I can choose to generate another task. Write a brief summary of a popular movie without revealing spoilers. Example, The Lion King. So like, again, this is a pretty creative task, right? Which was not specified by our prompt, but the model came up with it anyway. So in the Alpaca paper, they basically use this approach with GPT 3.5 to generate, you know, like 50,000 or so instructions paired with the inputs or outputs. And once you have access to this, all you have to do is fine-tune your base language model from step 1 with the data that you've acquired. So I can take this step 1 model and fine-tune it on a piece of text that looks just like this. Write a brief summary of The Lion King and the corresponding output, right? So you can see that in this way, if this API model is actually doing this, this task of coming up with the instructions well, I can extract that knowledge and you know, kind of induce the same behavior in my base model. Is that clear? So it's extremely simple. The budget you need for these attacks is not very high because, you know, any one of these queries on OpenAI's API does not cost that much. So you can imagine collecting 50,000 of these model-generated demonstrations. It cost the Stanford researchers only $600 to do this, and they just had a much better model after fine-tuning. So, you know, it's anyone can do this with GPT-4 even. Okay, and there was also this other model that is more recently released called Vicuna. In this model, they didn't use this self-instruct method. Instead, they relied on this website called Shared GPT, where people post their interactions with ChatGPT on a website. And so you can imagine that those interactions are very valuable training data. They generally do consist of instructions, and not only that, these are instructions that real people found useful enough to put into the model, right? So the distribution over these instructions is probably more useful than in the self-instruct case where the model is just asked to come up with random tasks. And they similarly took this pre-trained llama model and fine-tuned it on data that they got from Share GPT, and the resulting model is even better than this Alpaca model. So, you know, and there are many more models that have been released like this, which you know, use data generated by one of these huge language models to improve their own performance. So like, what are the legal issues of doing this? I have no idea. What does it mean for a company like OpenAI when it's so easy to do this? I also don't know. But it is very clear that these attacks are cheap and easy to run, and you know, like, we could do it in our lab right now if we wanted to. But I think the fine-tuning part, step 3 here, does actually require significant compute. Certainly not in as much as pre-training the model from scratch, but you would still need like some maybe 4 or 8 A100s or other beefy GPUs to do this. So we could do it. Is it worth the time? Maybe not, because Stanford already did. So anyway, yeah. Any questions about this part of the talk? Sorry, the lecture. Yeah. So this question is kind of separate from distillation. I think you're asking, like, in terms of the pre-training of a model, like, can you pre-train any 7 billion parameter model to be as good as Llama? So we will have a lecture next week on what are called scaling laws of language models, which researchers have trained many models of different sizes, different data set sizes, different compute budgets. And so there are now general trends on what you can expect if you train a model of this size on this much data with this much budget. Those laws are being revised all the time, so it's not clear how predictive they are, but there are some meaningful trends that if you wait till next week, you'll have an answer. But in this lecture in particular, the distillation process for something like this is very different than what we mentioned at the beginning of class. Again, here, you don't have access to any probability distributions. You're instead training your model to mimic the actual hard targets that are generated by the black box API model. All right, so the last thing I want to talk about today is a different type of attack against a very recent class of models that has been released. So this work is focusing on models that attempt to detect whether or not a piece of text is generated by GPT-4 or not. And obviously this is of huge significance to teachers who want to know if students have used GPT-4 for their homework, or you can imagine in an English class, this is really bad, right? Because you can go to GPT-4 and get an essay in 30 seconds and then just go about your day normally. But how does a teacher know if someone has used GPT-4 or not? Similarly, maybe you're an you're a malicious news organization, you don't want to hire any actual reporters. What if you just generate all your articles using GPT-4, and who's going to know, right? So this kind of detection is very important. So we've seen numerous approaches proposed to deal with this. Turnitin, some of you might be familiar with this website where you upload your assignments and then teachers can check if you plagiarized some other students' work. They recently announced this detection capability to see if someone has used ChatGPT or not. And they claim to have 98% confidence on detecting whether an assignment used ChatGPT or not. This is just blatantly false. There's no way they can do this with that confidence, but I guess it's it's good for marketing. OpenAI announced their own classifier to detect whether or not a piece of text is written by an AI. If you have seen some of the press around this release, you probably saw that the classifier does not work well at all, and it frequently detects human written text as AI generated and vice versa. Stanford released this thing called Detect GPT, which does a similar thing. And then there's this GPT-0, which was some undergrad's winter break project that somehow has raised millions of dollars of funding now for a product that literally does not work. You can try it out on their website. You will be surprised at, you could just inverse its predictions and do better. So Anyway, there's a lot of attention in this space, and clearly there's a lot of people who are willing to pay for services like this. But it's a very hard problem. So I think the best algorithm for detecting whether or not a piece of text is generated by an AI is watermarking. So this approach was proposed by this paper, Kirkenbauer et al., a couple months ago. And it can only be implemented by an API provider. So let's say OpenAI could apply a watermark to all of the outputs generated by their own language models. It's not a general purpose detector, right? So for example, it might work on GPT-4, but it may not work on Llama, just because it has to be maintained by one provider. Nevertheless, this is still good for, say, OpenAI to implement. Basically, how it works is some user types in a prompt to the model, and the watermarking approach will then, when the model is generating the output to this prompt, at every time step, it's going to partition the vocabulary into what they call green tokens and red tokens. And this is a kind of a random partition. And so the idea is that tokens that are in this green partition, you're going to upweight their probabilities during the decoding algorithm. Whereas tokens that are in the red partition, their probabilities are artificially downweighted. So the end result is that when you generate text with a language model that has been watermarked, if you know which tokens are green tokens at every time step, you can actually see that there's a higher frequency of green tokens in the generated output than there would be with an unwatermarked model. So you can see here that without a watermark, you get basically an equal number of red and green tokens. With the watermark, there's far more green tokens. And so if you have a setup in this way, you can then just do a normal statistical test to detect whether or not the number of green tokens in this output suggests that it came from a watermark model or not. So really, it's a very simple algorithm to verify whether or not a piece of text is generated by a watermark model. All you need is access to the vocabulary and this function that is partitioning the vocabulary at each time step. So even someone who is not OpenAI could verify whether or not a piece of text is written by this watermark model, provided those items are publicized. Yeah. Yes, this is a great question. So if you artificially upweight half of the vocabulary, this could lead to very undesirable consequences for the quality of the generated text. So I did skim over some details. Basically, if the probability distribution has a low entropy, which means it's very focused around one or two words, this method doesn't really do anything because you're more likely going to sample one of those high probability words anyway, regardless of the minor upweighting of these probabilities. This method actually comes into play more when you have a very high entropy distribution. So the model has many plausible choices. In these cases, some of those plausible choices will be sent to this red list, others will be sent to the green list. So that said, it does hurt the quality of the generated text, and this has not been well studied right now, to what extent it hurts the quality, but we've observed that it does hurt, and yeah, it is something to look at moving forward. Yeah.
Has there been any look in applications like steganography with respect to the model output?
Yeah.
Say you choose a specific tense of a verb, is the byte for that extra S encode some flag saying, this is model.
Yeah, so this, I think, is a we will see methods like this in probably the near future. I think that kind of class of methods is all related to what you might call content-based watermarking. So instead of artificially playing with the probabilities of certain words, you might want to just insert some sort of content that could be hidden into the generated text in such a way that it doesn't affect the meaning of the like what the model wants to generate, but it's still detectable somehow, whether it be through like tense or something more subtle than that. But yeah, I think, you know, this is an interesting research direction. No one to date has figured out what the best way to do this is. It's much easier in image world to hide these kinds of you know, like artifacts, but with text, it's yeah, not as easy. Other questions? Okay, so this watermarking paper got a lot of attention when it came out. You know, all the companies were very interested in implementing it for their own models. So like OpenAI has teams working on this, and Google, and so on. All the companies that have APIs for these large language models. One problem is that the methods are not robust to very simple attacks. So in my PhD student, Kalpesh found that you can just take a paraphrasing model, so a model that's trained to rewrite a piece of text. You can apply it to the output of any of these watermark language models, and suddenly you get a result that has a lot more red tokens than the watermark model. So as long as the paraphraser model comes from a separate external model, like it's not itself a watermark model, this attack is very easy to run. And if you go to Hugging Face, you can download like hundreds of different paraphrasers. You don't even have to download them. You can just use them with the web API to rewrite something that, say, was generated by GPT-4. So with paraphrasing, you have this, like if you're using a paraphrase generation model, you have to check if the content of the paraphrase matches the content of the original input, right? Otherwise, if you're warping the content too much, no one is going to want to use this, this attack. But it turns out that paraphrasers now are really good, and you can rewrite the sentences that are generated by GPT-4 with minimal quality loss while still evading these watermarks. So just to be clear, like, and I realize now when I'm talking about this that telling students this is probably not the best thing to do as a teacher, but you know, whatever. I doubt any of you are in classes where this could be very useful anyway. It is very useful for a paraphrase model to have two properties if you're going to use it in this kind of attack. So one of them is you might want the paraphraser to be controllable, in the sense that you might want to make as few changes to the input text as possible in order to evade the watermark. This could allow you to, you know, make minimal changes to the meaning of that text as well. And secondly, you might want your paraphraser to be aware of context not only at the sentence level, but also at the full text level. So very often in these kinds of setups, a user will provide an input prompt to the model, and the model will generate an output. And so you might want to have access to the prompt when you're paraphrasing the text, in order to not make too many changes that might, you know, invalidate the instructions in the prompt somehow. So for example, let's say I have a prompt like write a story with 4 sentences, right? I might not want my paraphraser to merge 2 of the sentences together because that would invalidate the prompt. Okay, so I'll skip over this. Basically, we build an external paraphrase model, and we use it for the purpose of these attacks. And we evaluate these attacks over several different models. So this is just with GPT-2, the extra large version. You can see the performance of GPT-0 is terrible here. So I should mention that when you're measuring the performance of any of these detectors, it's very important that you have a low false positive rate, because you can imagine in this academic plagiarism setting, you almost never want the detector to fire that, to say that a human written essay was written by an AI, right? The consequences of that are disastrous. So we fixed this evaluation to have a 1% false positive rate. And so now we're trying to evaluate, how good is this at detecting the AI-generated text at this fixed rate. So watermarking is 100% accurate. And of course, this depends on how long the input text is. You can imagine that if the text is short, there are just fewer tokens, so the statistical test may not be as reliable. With paraphrasing, you can see that watermarking's accuracy drops quite a bit, to the point where it's probably not usable in any practical setting. Detect GPTs goes down from like above 50% to under 10%. So this is a huge drop. And we observed this trend on GPT-3 as well. We haven't tried on ChatGPT yet, but I imagine it's quite similar. So currently no methods are robust to this simple paraphrasing attack. That said, we come up with a hypothetical defense that OpenAI may be able to deploy that is kind of orthogonal to watermarking. It's very simple to explain. So basically, let's say you're OpenAI. You store all of the inputs and outputs that you have generated in response to user prompts in a giant database. So, ChatGPT might have had 1 billion or more queries at this point. So let's say we have 1 billion items in our database. Now, let's say a teacher wants to detect whether or not this essay was generated by ChatGPT. We can do retrieval. So we can the teacher can feed in this student's essay to this detector, and we can do retrieval over this entire database of 1 billion generations to see whether or not any semantically similar essays were generated by the API. And of course, now you need to decide how you're going to measure the semantic similarity of two things, and we have some different methods for doing that. But this is actually very effective and robust to this kind of simple paraphrase attack.
If you do something like generate engrams of some type of text and then like hash those
as a defense?
to detect subsections of text that have been generated by
Oh, yeah. This is if you want to detect like parts of, that might be a useful way to go. Or you could do retrieval on these kinds of chunks if you have a way to detect them. Perhaps the Bloom filter idea is far more efficient than that, but that's a good point. So let's just look through this retrieval-based idea. So let's say there's several different prompts that are fed to ChatGPT, including one by a malicious student who wants to use the answer to this prompt as, say, their essay that they're going to submit. So you have this huge database of responses, and now the malicious student knows that there's some detection algorithm going on, so they feed the output of their query to a paraphrase model. So now they get something like this, and they might be happy that they've evaded detection. But a teacher can feed in their paraphrased input to this retriever. The retriever will retrieve semantically similar generations, and it'll have a score for each generation. So if you have a threshold by which you decide that, okay, anything scored above this threshold will be detected as AI generated, and otherwise it will be detected as human generated. This is a very simple approach to tackling this problem. So high level conclusion is that this approach does seem to be robust to this paraphrasing attack, but the caveat is that we have not tried it at 1 billion generation scale database. Only OpenAI can do this at this point. So it's unclear how this will scale. We tried it on up to 15 million generations, and it seemed to scale pretty well, but of course that's like 2 orders of magnitude less than what might be practical. Yeah. Yes, and this is only, just like watermarking, only applicable to the language models that are served by a specific company's API.
So the watermarking can be implemented by individual companies individually, and still like companies can release the watermark function.
Yeah.
The companies will be sharing the data with each other.
So in watermarking, it's true that the companies can release the information needed for anyone to verify the watermark, but in practice that will never happen, because as soon as you release that, anyone can devise methods to attack that particular watermark. So there's all of these kinds of considerations. Again, these are great questions. These are this is a very new field that just emerged right after ChatGPT was released. I'll just, actually, maybe I'll stop here. So there's a lot of limitations of this retrieval-based approach as well that need to be figured out for it to be practical. You can check out this slide later offline if you're interested. Next week, we will talk about scaling laws of language models, so see you then.
Thank you.
Yep.